Good morning, good afternoon, good evening, everyone. We are delighted to have you all online. Today, we're going to have our presentation, joint seminar series. The presentation is going to be given by Andrew from the University of Nevada in the US. The title of the talk is Can Alternative Transfer Mechanisms, ATMs, Alleviate Water Scarcity? If you don't mind, I will just proceed with the introduction of Frank. And after the introduction, Frank, you have, let's say, 25 to 30 minutes, to give your presentation. And thereafter, we will have a Q&A session. Andrew is an assistant professor of economics at the University of Nevada. His main area of research includes environmental and natural resource economics, institutional economics, applied econometrics, and water policy. The primary line of investigation considers how institutions, rules, norms, and regulation are adopted and subsequently influence human behavior and resource conditions in river basins. Much of his work concerns the governance of groundwater and surface water resources, with a focus on the definition and evolution of property rights and other legal processes that affect water management, in particular water markets. Some of his recent work examines the efficiency and distributional implications of groundwater management, with a focus on water market dynamics and managing impacts from fallowed lands. Andrew was a Fulbright Fellow and worked in Germany and on projects related to climate change, energy, river restoration, and water pricing. He holds a PhD from the University of California, Santa Barbara, and a bachelor in Panama College. Once again, colleagues, it's good to have you. Andrew, the floor is yours. Thank you very much.
Okay, thank you very much as well. I'm going to try to share my presentation right now. So, can everybody see the slideshow now?
Yeah, we can.
Okay, excellent. So thank you again for having me. My name is Andrew Ayres. I'm going to be presenting Can Alternative Transfer Mechanisms Alleviate Water Shortages, which is joint work with Catherine Wright at Hillsdale College and Brian Leonard at the University of Wyoming. And that's a bit of a mouthful for a title, but really what we're going to be talking about today is water rights in the American West and how contracting over those water rights for leases can provide benefits, but also may have pitfalls, okay? And we're going to talk about that over the course of the next 25 or so minutes. So, Western water. Water in the American West, especially in the Colorado River Basin, is becoming more scarce, and the supply of this water is becoming more volatile due to climate change. The Colorado River Basin is the major sort of supply source for most of the American Southwest, including many hundreds of thousands of acres of agriculture, as well as major growing urban centers like Phoenix in Arizona. Okay, so while supply is becoming more volatile, populations are also increasing. And at the same time, agriculture still uses about 80% of the developed water in the American West, despite large price differentials in water between agriculture, where generally the amount of value generated by the marginal unit of water is low, and urban settings where the amount of water generated by the marginal unit of water is very high. Okay? So all of this leads us to believe that in the future, right, especially under strained supply conditions and with growing populations, more water will need to be moved from agricultural uses to urban uses. Okay? Just one example, recently in the San Joaquin Valley, long-term leases and permanent transfers of water from agriculture to growing urban areas have enabled more than 1 million new residents, or are expected to enable more than 1 million new residents in the San Joaquin Valley by 2040. We anticipate that movements like this are going to be required more broadly throughout the American West, which raises the question, under what conditions is that water going to get moved? Will it get moved efficiently, or are we going to run into problems with this? Okay. So historically, there have been some frictions in moving water out of agricultural uses, especially in rural areas, into water supply systems for urban developments. And in particular, irrigation districts formed in the American West and their members fear a process that's been dubbed buy and dry. Okay, so urban utilities sometimes will come into rural areas, buy up water rights from irrigation districts, and the land that was previously irrigated with that water will end up becoming dry, fallow ground, or otherwise will just not have a new use. Okay. In some, permanently moving this water out of these irrigation districts has reduced economic activity and the economic vitality of those rural areas. Okay? Some pecuniary externalities dominate the discussion around these transfers. For example, what happens to labor when the water moves away? What happens to downstream processors of agricultural commodities? And in many cases, right, people fear what they've described as the Owens Valley syndrome, where this alludes back to a major water transfer from the 20th century in which Los Angeles went and bought quite a bit of water out of Owens Valley. The lake bed dried up, and ultimately the economic vitality of the region suffered, and large dust storms became a major sort of physical externality of that process. So kind of zooming out a little bit and thinking about not just water, but what's the sort of economic import of these questions we're asking, right? There's a large economic literature on efficiency and adaptation to disturbances, okay? So market solutions, such as the development of water rights and subsequent markets related to those water rights, have been identified as a solution to common pool and externality problems as early as 70, 80, 100 years ago. And in fact, right, markets are one of the main mechanisms that we as economists think might provide some benefits in terms of adapting to disturbances and helping to coordinate and provide a framework for economic organization in the presence of things like climate change disrupting supply of water availability, or growing populations in urban centers shifting the demand curve for water. Okay, so we're going to, in the course of this talk, evaluate the extent to which the market mechanisms that have been developed until today are capable of overcoming concerns about buy and dry and ultimately facilitating the reallocation of this water from lower value agricultural uses to higher value urban uses. In response to concerns about buy and dry, right, the decline of rural communities in response or as a result of moving water out of irrigation districts, one solution has been proposed, which is alternative transfer mechanisms. So instead of permanently buying water from a rural irrigation district and moving it in the long term every year to an urban settlement, we might think about structuring a contract differently. And when we think of an alternative transfer mechanism, what we're thinking about is farmers or districts, if they own the water, retaining ownership of the water rights locally, right, in a rural irrigation district, but instead drawing up a series of contracts with an urban water supplier over land use within the district. In other words, the public water supplier from the urban municipality will come out and write a contract that says, especially, during a period of drought, I might pay you a little bit of a little bit of money for you to fallow your land, make the water available, and then I take it in that year. But in other years, when it's not a drought, you would keep the water and you would continue farming in the rural area. Okay, so these contracts are often temporary and they're flexible. We avoid a lot of the barriers or the challenges or the frictions that come along with permanently moving water out of an irrigation district. And oftentimes these contracts will involve side payments to communities to help offset some of these pecuniary externalities or offset some of the economic decline that is associated with taking water out of rural communities. So all of that sounds great, right? The urban water supplier gets water when it really needs it during a drought. The rural irrigation district gets to keep it the rest of the time. So in other years that are non-drought years, we avoid the economic decline in the rural area and we still get to have growing urban populations. But the catch is that these contracts are ultimately incomplete because where cities value water, they're actually paying for land use changes. And in many of these contracts, the measurement of the water that's made available is not very precise, okay? And that is exactly what we're going to be discussing over the next 20 to 25 minutes, okay? So our research questions for this effort are: 1, do alternative transfer mechanisms deliver the expected water savings that parties anticipated when they drew up these contracts? And 2, can the use of satellite data improve evaluation of water markets and transfers? To answer these questions, we're going to leverage parcel level data on consumptive water use. So in other words, evapotranspiration has been derived from satellites and models based on those satellite outputs. In particular, we're going to be using data from the OpenET program. If you're not familiar with it, I highly recommend a Google. It provides high-resolution satellite-based imagery of evapotranspiration across the entire American West. We're also going to use parcel-level info on fallowing calls in the Metropolitan PVID fallowing program, which I'll describe in just a moment, to get causal estimates of the effect of a call, in other words, the enactment of a contract, on water consumption within the district. And we're going to compare the estimates of saved water from Metropolitan to those from our analysis and decompose any differences between them. So our case that we're going to study to answer these questions is the Palo Verde Irrigation District and Metropolitan Water District Fallowing and Forbearance Program. It's the longest running such program in the West, started in 2005. And it did have a pilot in the mid-1990s, but really the program got started in earnest in 2005. And so essentially what's going on here is that Palo Verde Irrigation District, delineated here in yellow, is abutting the Colorado River. It's an agricultural irrigation district, and it has very senior rights on the Colorado River. So even during drought, Palo Verde Irrigation District is going to get water. And Metropolitan Water District is the largest municipal water wholesaler in the West. They provide drinking water, wholesale drinking water to places all the way from Ventura on the northern part of their service territory down to San Diego on the southern portion. And so essentially what's going on is Metropolitan is looking for a supply of water that they can rely on during drought, but they don't want to completely buy out water rights from Palo Verde Irrigation District. Okay. So this fallowing and forbearance program, let's go over some of the details, right? There was a single initial enrollment period in 2004 when farmers could say, I have some land that I'm irrigating. I'd like to enroll it in this program so that when a drought rolls around, I can get paid to fallow it and you take the water. However, there were some constraints, right? No farm could enroll more than 30% of its own acreage in the program, and there was a similar cap at the irrigation district level. The parcels had to be irrigated at the time of enrollment, okay? And once they're enrolled in the program, Metropolitan Water District can issue a call, if they choose, twice per year. So there are going to be 2 irrigation seasons that we're going to keep track of in our analysis, that requests that parties who have written a contract, right, who have enrolled their lands, would fallow a specified percentage of their enrolled acreage, and that water would then subsequently be made available to Metropolitan. Okay. Farmers get paid once when they enroll their parcels, and then again they get paid if they're called on to fallow. Okay. Metropolitan goes and they verify the fallowing visually to make sure that the parties that are being paid to fallow land, in other words, take it out of agricultural production, are indeed not irrigating that land anymore. And then Metropolitan accesses that saved water via an end-of-year river accounting process on the Colorado. Okay. And so just a little bit more background here is that, right, Palo Verde Irrigation District has a very senior right. If they save water, there are agreements with other users on the river that guarantee that that water would flow down the priority line so that Metropolitan is able to have access to it. All right, so the last piece of the introduction here is how do we actually measure how much water gets saved? So the first thing we're going to talk about is how Metropolitan measures these water savings. And they use a fairly simple approach, okay? They basically calculate that the amount of water saved in any given season is equal to the total diversions in the district. So how much water came into the district minus return flows. So how much water was not actually used in the district, but then re-entered the river, divided by the total irrigated acreage. So essentially they calculate on average, how much water is being used consumptively on every parcel in the district, or on every acre in the district, and then they just multiply that by the number of acres they paid to fallow, okay? So in a typical year, Metropolitan is going to estimate that roughly 5 acre-feet of water are conserved per acre, okay? And right on average, over the years they've been running this program, they estimate that they saved about 96,000 acre-feet of water. If you aggregate that from 2005 through 2021, it's about 1.5 million acre-feet of water. But there are some frictions or some rubs in this calculation and its underlying simplicity, namely that, right, water use varies throughout the district. Not every parcel is made equal. Some parcels may be using more water than others. And this calculation also assumes that when, right, Metropolitan calls on an irrigator to fallow, that 100% of the water that they were using on that parcel is now made available further down the system. So we're gonna sort of critically investigate those two assumptions in our work and show that, right, the amount of water that we think is actually being saved doesn't necessarily line up with this simple calculation. So now I'm gonna shift gears and given you the introduction to the program, right, where we're studying this, what our question is, and now I'm gonna start talking about the data and our empirical approach. So the first very important piece of data we have is indeed the evapotranspiration on these agricultural parcels. So again, remember, what we're getting here is a measure of how much water was consumptively used on every parcel within the district, and therefore, right, how much water could have possibly been made available if those parcels were not irrigated as part of this program, okay? To do that, we're going to use the Operational Simplified Surface Energy Balance Model published by Sinai et al. And in more recent years incorporated into the OpenET platform, which is going to return for us a daily total actual evapotranspiration geospatially. Okay, so we're going to be able to use these data to compute for every different parcel, every land parcel within the district, how much water was consumptively used. And right through sort of evaluation of the accuracy of these models, right, ground truthing using on-site ET measurements suggests that local R squared between on-site measured ET and ET estimates using the satellite data could be as high as 0.88 across study sites. So we believe that these sort of satellite-based methods for getting at ET are fairly accurate, although they, of course, are not perfect. So this image here, these images here will give you a little bit of a sort of visual representation of what the data look like, right? Geospatially, we're able to map out evapotranspiration throughout Palo Verde Irrigation District, which is what you see here on the left. And we have a fine enough spatial resolution that we're basically able to pretty accurately allocate evapotranspiration on a parcel by parcel basis within the district. Okay, that's what you see here on the right. So this is going to be our main outcome of interest, right? How much water are we using? And we can plot this, right, monthly within the district. And here are some comparisons as well. So the blue line here is showing the OpenET estimate of within Palo Verde Irrigation District, what's the total consumptive use by month? And if we're peaking in the summer, right, where it's very hot, a lot of water is being applied for irrigation, right, to keep plants alive and growing. And you'll notice that the OpenET estimate is a little bit lower than the red line or the blue line, or the green line, both of which are based on Metropolitan's estimate of consumptive use, right, which was that simple equation I showed a minute ago, just diversions minus return flows divided by irrigated acreage in the district, okay? We can also plot this across years, highlighting the same comparison here, right? In most years, that blue line, the evapotranspiration estimates from the satellite data lies below the green and red lines. So right off the bat, the OpenET data are suggesting we might not be consumptively using as much water in the district as Metropolitan thinks we are, okay? And we can also break this out by crop. Okay, here we're just looking at the OpenET data, but we've been able to separate out how much water is being used consumptively on these fields by crop type, okay? So alfalfa is king in terms of water use, as well as in terms of irrigated acreage out here. but also citrus, cotton, grass, these evapotranspiration estimates are pretty much in line with what we might expect. Okay, so just one more quick note on understanding the differences here, right? We basically got our ET data from the satellites, and we've got what we might call metered use, okay, that's metropolitan water district sort of simple calculation, okay? MWD has historically used aggregated estimates of total diversions less estimated return flow to come to a measure of average consumptive use per parcel, okay? And USPR has recalculated that in a different measure using their own crop coefficients, but we're going to treat those two sources as sort of mostly the same. But the ET methodology or quality is also going to be constrained, right? This isn't perfect either. The quality of the ET data is constrained by the resolution of key inputs like crop choice and surface temperature, okay? But we're going to compare and contrast these over the course of the next 10 or 15 minutes here. And the way we're going to do that, right, is we're going to create a sample of the district using the ET data, and we're going to look at every tax parcel within the district boundaries, and we're going to assign it an estimate seasonally of how much ET it used based on the satellite data. Okay. So the other big piece of information we need for this study is which parcels, right? Which farmers got called to actually fallow as a result of this program. Okay. So we're going to collect these data from the annual verification reports issued by the Metropolitan Water District, right? They write up these reports in order to document, right, for the accounting on the Colorado River, how much water did we actually save as part of this program, right? And they're using their own simple calculation to do that. But we're going to take from these reports digital maps, digitized maps, I should say, of all of the parcels that got called within the district. And we're going to use that to understand, right, across these parcels, who got treated or who wasn't treated, meaning they were called or not called in any given year. Okay. So our empirical approach is going to be fairly simple here at a base level, right? Our estimand, what we want to know is how many acre feet of consumptive use were saved per fallowed acre under this program. So we're going to estimate three different equations. In the first, we're just going to estimate acre feet of use on a parcel and control for acres of that parcel on the right-hand side, okay? Also including parcel level fixed effects and season of sample fixed effects. So that's your gamma and your tau there. We're also going to estimate this model using acre feet per acre as the outcome variable, where, right, when you get called, we're going to estimate how much the acre feet per acre declined on your parcel. And then we're also going to estimate this in logs, right? That's equation 3 here. And equation 3 is going to be particularly useful for comparing our results, right? What percentage of water savings resulted from a call on these parcels to the MWD results, okay, the metropolitan results. So what we're setting up here is the first is that, right, we're going to do a two-way fixed effects estimation, and then we're also going to do an estimation based on the new differences in differences literature, okay? And that's what I'll talk a little bit about here. Basic two-way fixed effects via OLS regression, right? We can control for both parcel and year level fixed effects, fixed determinants of water use, okay? So these are the determinants on every given parcel across years or across all parcels in any year of how much water is being used, right? And we'll basically be evaluating average changes in water use on a parcel basis for parcels that were called, in other words, told to fallow, versus parcels that were not, okay, in that particular season. Well, we can also, as we know from the new differences in differences literature, right, if we have heterogeneous treatment effects and staggered treatment timing, which we likely have in this case, right, then the two-way fixed effects estimator might not give us the true difference in difference result, okay? So we're also going to estimate this using a robust difference in difference estimator. I won't bore you with the details, but basically what we're going to do is we're going to consider each cohort of called parcels in any given season separately, and we're going to evaluate the average changes in water use on those parcels relative to parcels that either have never been called in the entire sample period or were not called up until that point, okay? So what we're going to avoid doing there is comparing a called parcel, right, the water use on a called parcel to a parcel that had been called previously, but in that particular season was not called, okay? So there are good econometric reasons for why we might want to do this, and I'll just explain the differences in the results later on, okay? So sticking with our baseline two-way fixed effects estimator, right, we have estimated all three of our models, and you can find the results here in this table, right? This regression is being estimated on a season basis. So these coefficients you're seeing don't correspond to annual savings, but I'll talk about that in a minute. Basically, what we find is that per irrigation season, right? So this is a 6-month period in PVID, right? This is the season during which, right, you might be growing one crop as part of a rotation, and the season during which a call from Metropolitan would be in effect. We find that the calls on average reduce consumptive water use on parcels by about 1.2 acre-feet per acre per irrigation season, right? So this is equivalent to about 2.4 acre-feet per acre over a year, right, if the parcel happened to be called for an entire year. Okay, and the log specification suggests that we have up to about a 74 to 80% reduction in consumptive use relative to parcels that were not called in that particular season. Okay, so you can see already here we're moving towards a comparison with Metropolitan's results, where we're finding that although these water savings are substantial, they might not be 100% of the water use on any given parcel. Okay. So moving on from the two-way fixed effects results, right, one of the things we need to think about both for the two-way fixed effects as well as for the DED is, right, are enrolled and unenrolled parcels more or less the same? We find that there are some small differences, and you can see right here in bullet points how enrolled and unenrolled parcels vary on average. For example, enrolled parcels tend to have a little bit more alfalfa and grass than unenrolled parcels, a little bit less cotton and citrus. Right, this kind of checks out. It's not likely that someone's going to enroll an orchard in a temporary fallowing program, but largely these differences are fixed, and so we're fairly confident that our parcel fixed effects are going to pick up most of the sort of baseline differences between these parcels. And what we really need is for the parallel trends assumption to hold. In other words, before the program was implemented, we want to be fairly certain that the enrolled parcels and the unenrolled parcels were on the same trend with respect to water use, okay? And we find some support, right, for that assumption. What you're seeing here are the pre-trends, so prior to the introduction of the program, acre-feet per acre, consumptive ET usage on enrolled and unenrolled parcels. There is a baseline differential, right? Enrolled parcels use a little bit more water on average. And again, these are seasonal numbers here, but the trends are fairly similar, right? Fairly flat differential moving into 2005, where we have the introduction of the program. Okay, so now I'm going to present results from our robust difference in difference estimator. And what we have here on the left, right, is right difference in difference estimates of water use on called parcels versus parcels that either were never called or had not been called, leading up to the point at which a particular cohort of parcels was called, okay? So what you really want to pay attention to here is the value of the estimate at 0.0, so the rightmost point on both of these graphs, okay? So what we find is that if you estimate this in acre-feet per acre, as we do at the season level on the left, we calculate out about a 64% reduction in water use in acre-feet per acre. And on the right-hand side, we're estimating this in logs, and there we find about a 67% reduction. So, right, this alternative, robust method for estimating treatment effects using the new difference in difference literature suggests that we might even be saving a little bit less water than the baseline two-way fixed effects estimator suggests we are, okay? And certainly less than Metropolitan Water District assumes that we're saving based on their simple calculation, okay? So now that we have our estimates, right, we can actually compare water savings under the program using different approaches for calculation. And there are a lot of lines on this slide, but I really just want to draw your attention to, right, the green line, which is our estimate using, that says two-way fixed effects. It should say difference in difference, okay? Our difference in difference estimator and the remotely sensed satellite ET estimates. And the blue line here at the top of this sort of collection of lines, which is sort of what we'll call the simple Metropolitan Water District estimate of how much consumptive water use are we saving. So you'll see there's a fairly large difference there. And some of these intermediate lines, right, we're mixing and matching. Are we using the DID estimator with MWD's estimate of ET? Are we using the satellite ET measures with MWD's approach for estimating consumptive use, right? But the point is, right, there's a large difference. Part of it is explained by measuring ET differently, and part of it is explained by taking account of the fact that not all parcels are created equal within this district, okay? From these different estimates of water savings, we can compute, right, a potential overestimation of savings by metropolitan. So again, here I want to just draw your attention to the green line, which is the DID estimator with the open ET data, suggesting that in some years, right, we may have overestimated water savings in Palo Verde as a result of this program by upwards of, right, 40,000 acre feet. And we can compare that to the orange line, which is the DID estimator, but using, right, metropolitan's estimates of how much evapotranspiration is occurring on every parcel. So in other words, we are using a different counterfactual, right? But we're using metropolitan's measurement of how much ET is happening on these parcels. And that explains about 30% of the difference, or the overestimation of potential savings. So you're looking at it here year by year, but if we calculate this or aggregate this over years, we find that, right, overestimation across a little bit over 15 years of this program may exceed 500,000 acre feet of water, right, under our sort of like most pessimistic scenario, here the green line. But if you just change, right, if 30% of that difference can be explained by differences in how we measure ET, okay? And I'm a little bit over time, so I'm going to speed up now, okay? But one of the big takeaways here is that any way you slice it, right, even if you use MWD's process of calculating savings, but you use ET measurements, right? So you assume there's less ET, but we're just sort of naively saying all the parcels in the district are the same and they reduce water use by 100%. You still might come to the conclusion that overestimates the amount of savings from this program exceed, right, annual use of some states on the Colorado River. All right, so we've got some differences here. These differences imply a little bit of overestimation from the program, okay? More specifically, right, one of the main sources of variation is that the difference in difference estimator suggests about a 70% reduction in water use rather than 100%. So that's a bit of a big deal, right? But the other main source of variation is simply how we're measuring ET, okay? So if you use the Metropolitan Water District estimates of how much ET is going on in these parcels, that reduces the gap by 30%, okay? So 30% of the difference is due to potentially, right, just how we measure ET using the satellite data, which we believe may be more accurate versus this sort of coarse estimate of diversions minus return flows. And then the rest of the difference might be made up by, right, thinking about the different counterfactuals, right? Not all parcels are made equal within the district, okay? So, right, what makes up the difference, right? Different counterfactuals matter, right? The DID estimate is based on an estimate of what would have happened on called parcels if they had not instead been called, right? Whereas the Metropolitan Water District approach to measuring water savings here just compares those parcels to what actually happened on uncalled parcels, okay? There's another potential explanation, which I'll talk about very briefly right now, for why we're still picking up residual ET on parcels that were called, right? We're only seeing water use decrease by about 70%. And so some explanations for that might be spillovers from parcel to parcel, right? If you're fallowed, but your neighbor is still irrigating, does some of that water, right, seep over to your parcel and get evapotranspired? And there are some other mechanisms I'll talk through very quickly, okay? So I'll skip over non-additionality of calls. Right, we find that it's not likely that farmers were taking lands that were previously not irrigated and then enrolling them in the program and having them be called and getting paid for it, right? The fallowing rates in the pre-period on parcels that were eventually enrolled was less than 5%, right? So that's probably not a major explanation for why we're finding these differences. When we think about seepage or spillovers from one parcel to the next, right, we're asking the question, does continued irrigation on a neighboring parcel cause residual ET on a called parcel? The open ET data are of high enough spatial resolution to test this, and in ongoing work, we are indeed testing this potential mechanism. And then the final reason why we might still be finding some differentials here is non-compliance with the restrictions. And here we don't necessarily mean deliberate non-compliance, although that is also potentially happening, right? But really, we're thinking about the fact that it's important to account for uses of water on a given parcel that are not irrigation per se, but nonetheless represent real water use. So one example might be the planting of cover crops, and even if you don't deliberately irrigate them in the way you might irrigate a cash crop, right, they're going to use some water, they're going to have ET requirements. Another use of water on some of these parcels might be soil flushing, okay, to remove salts from the soil and render the plot more ready for planting in the subsequent season, or native vegetation establishment if people are not sort of maintaining a bare fallow on their plots. And in particular, we think soil flushing might be one potentially meaningful source of continued ET on these parcels, because a study from a nearby irrigation district in Arizona found that even on bare fallow parcels, okay, capillary rise of saline groundwater resulted in anywhere from 1/3 to 1/8 of the irrigated ET being retained on fallow. Okay, so even if you're not soil flushing, right, shallow groundwater resulting from the previous season's irrigation can then, through capillary action, rise to the surface and evapotranspire, or evaporate in that case, right? And that might be part of what we're picking up in our estimates. So one last little piece to layer on here. All right, so we've estimated here that Metropolitan may be overestimating the amount of water that they're saving. If that's true, and if Metropolitan is not receiving as much water as they otherwise would have imagined due to this overestimation, we can calculate how much more are they actually paying for this water than they initially anticipated paying for it, right? So based on Metropolitan's estimates, they may be paying as little as $143 per acre foot of water availability during drought. That's a very nice price for a public water supplier looking for additional water supply in the midst of a drought, okay? But if you take our estimate seriously, right, and you believe that the DID estimator produces a better estimate of the average treatment effect of a call, and if you believe that the ET data are a more accurate estimate of consumptive water use, then MWD's sort of coarse diversions minus outflows approach, then MWD might be paying as much as $306 per acre foot. Still not terrible, but a significant increase in effective price over what they might have anticipated when they put together the program, right? And let's remember that the program cost through 2021 has been over $210 million. So a couple quick takeaways, right, from this study. Remote sensing of ET opens up new frontiers in water accounting and contract formulation, okay? We would imagine that moving forward, right, new alternative transfer mechanism programs might use OpenET or other satellite mechanisms, methods to measure ET, at least as a check on other alternative methods for calculating ET. These methods for ET can provide greater spatial resolution, and they can also ultimately just help us do a better job of reallocating water in such a way to avoid transaction costs, right? They can help us do a better job of asking how much water are we really getting, when are we getting that water, and ultimately being able to write better contracts over this will help further along better pricing, which is key to facilitating reallocation of water in the West. And in our particular case, right, we found that using a different ET estimate and a more robust difference in difference estimation reduced estimated savings by as much as 50%. 30% of that difference can be accounted for by the measurement differences. But really, I think one of the major sort of takeaways here is that the reduction in water use is robustly less than 100% on these parcels. And we talked through a couple of mechanisms for why that might be. And in ongoing work, we're doing more empirical we're making more empirical efforts to kind of understand what mechanisms might be most likely. So with that, I'll stop and we can have a little bit of a Q&A, I think.